Okay. So last time we started with the transmission line and we discussed about its contents and what is required and which derivation is required and which formulae are required, everything. We discussed about the type of transmission lines with an basic कि भाई कैसी होती है transmission line. It is nothing but for an example we can consider coaxial cable fed with generator side and providing power on the load side. We also discussed with the different types of transmission lines. Okay, you need not to go for the formulae for each and every type of transmission line, that is not in your syllabus, but yes, this particular rectangular waveguide you will discuss in a next year semester 1 subject, radiation and microwave techniques, okay, in detail. Then about line parameters, we considered a parallel wire presentation which was broken into differential sections of delta z long, and we have observed the individual section do have its own resistance, inductance, capacitance and conductance. So we do have its own characteristics and parameters. Those parameters are nothing but a primary parameters and secondary parameters. So in primary parameters, we do have resistance and inductance and conductance and capacitance. We do have their understanding. Okay, we cannot get rid of resistance, inductance, capacitance and conductance because those are the material properties. Okay, we do also have the secondary parameters. First one is characteristic impedance, and we do have its definition. Characteristic impedance, whenever we say that impedance or reactance, always we do have the frequency associated with it. So you can observe the characteristic impedance of any transmission line do have the resistive impedance and conductive impedance R plus j omega L and plus upon G plus j omega C. Okay. Then propagation constant gamma, it is also called as coefficient, and this indicates how your wave is propagated along the line. So it is represented as gamma is equal to under root z up into y, or we can say that under root r plus j omega l into g plus j omega c. R plus j omega l is an series impedance, okay, and y is a shunt impedance. Also, in unit number 5, we are going to represent gamma, which is nothing but propagation constant, as a result of alpha plus j beta, where alpha is attenuation and beta is phase constant. So attenuation constant alpha determines the reduction or attenuation in voltage or current along the line, and its unit is Nipper per kilometer. It is represented in this way. We are not going to look into the derivation how we arrived this formula, but yes, this formula and phase constant formula, we are going to use these two formulae in unit number 6 in while solving the numerical. Then wavelength, it is defined as a distance. Okay, do remember that it is a distance between two maxima or two minima or a phase shift of 2 pi radians. Okay, so lambda is equal to 2 pi upon beta. And next parameter is phase velocity of propagation, Vp. Velocity is defined as distance upon time. So we can say that lambda upon t, 1 upon t is f, and lambda is 2 pi by beta. So we can say that, okay, 2 pi f is omega and omega upon beta. So phase velocity or velocity of propagation is omega upon beta. Then intrinsic impedance of medium eta. Specifically, we are going to use this formula and the loss tangent formula in unit number 6. But for the sake of representation and everything comes together, so we have put this formula and the loss tangent formula in this slide itself, so everything will be in connection with each other. Then skin effect. Okay, now the skin effect is defined as the rate the rate in which the wave has been attenuated by the amount 1 upon e, or approximately 37% of its initial value. Okay, means what? If we have a boundary and certain wave is getting incident on this boundary of some materials, okay, we will have some kind of material. Definitely part of the energy will be reflected and part of the energy will be refracted inside the material. Okay, we are talking about the electromagnetic waves. And if I say that, okay, we do have 100 power inside the incident wave, so the depth inside the material, okay, it is nothing but the skin effect, where where the wave has been attenuated by approximately 37% of its initial value. Okay, 37% से वो reduce होगी, attenuated by the amount 1 over E. Okay, तो मतलब 37% से रिडक्शन होगी, रिड्यूस होगी एम्पलीट्यूड, या फिर आई विल से दैट ओके it reaches to the 63% of its original value. 37% reduction, it is as good as reaching to the 63% of its value. So I will say that कि जहां पे उसकी value 63 होगी, going from 100 to 63, this much depth is called as your penetration depth. Okay, penetration depth, and this has very good practical implementation, or I will say that example. Okay, we will first put it into the formula. So in general, the penetration depth 1 upon, sorry, penetration depth delta is given as 1 upon alpha, and alpha has this relation. And the practical example, we had Reliance CDMA handsets. Okay, and lots of people were using these handsets in the year of 2006 to 2008. Okay, and lots of क्या कहते हैं उनको, marketing executives. Okay, marketing executives were given with these handset because calling the free था, Reliance to Reliance. Okay, what they used to do कि भाई बॉस ने बॉदर नहीं करना चाहिए, what they used to do, they were while talking on the phone, they used to remove the battery from the handset. Okay, the problem with those Reliance handset was, if you are removing battery from the handset while call is going on, and if the another person tries to call you, they get an tune of phone is out of coverage and not the phone is shut down. Okay, phone is turned off, ऐसे ट्यून नहीं आती थी, ऐसे अलर्ट नहीं आता था. Okay, so they what they used to do कि भाई कॉल जब चल रहा है तब बैटरी निकाल दो, मतलब if anyone is going to call you, it will say कि भाई phone is out of coverage, this kind of alert will be sent. And and if this is not possible, I don't know, if this is not possible, then they were used to carry tiffin boxes with them. Okay, so what they used to do, inside a stainless steel tiffin box, okay, inside a stainless steel tiffin box, they used to put their handset. Okay, और इसकी वजह से क्या होता था, इसका लीड लगा दिया उन्होंने. ओके, लीड भी लगा दिया. When they used to keep their handset into the tiffin box, the electromagnetic wave coming from the mobile tower was not able to penetrate to sufficient depth inside this tiffin box, and this mobile handset actually practically was kept out of coverage, because these radiation which are incidenting on the boundary of the surface of your tiffin box were not so powerful that they can penetrate this stainless steel box. Okay, so tada, they used to have their phone live, they need not to turn off their handset, and still their phone is out of coverage. So if boss asks you, "Hey, why you have kept your phone out of coverage?" No, boss, you can check my handset. I didn't switched it off. No. But on the back end, they used to put their handset inside a stainless steel container where the penetration depth was not sufficient so that your mobile handset will get your tower, will get your range. Okay, so penetration depth वहाँ पे कम थी. Similar kind of experiment you have studied somewhere in school time, that is called as Faraday's cage, but that time you do have some cancellation of vectors. If you remember, uh, if you have a mesh kind of structure, okay, mesh kind of structure made up of iron or copper, okay, your electromagnetic radiation cannot penetrate into it. But I will say it is not able to penetrate because there are cancellations of the some of the vectors due to symmetry conditions, as well as you can observe we do have small rectangle. Okay, so I can say that due to Stokes theorem also. Stokes theorem says that magnetic field magnetic field intensity relation observed over the surface with the closed loop path of that surface. Okay, boundary of that surface. Okay, skin effect. So all of the radiation always is available along the surface of the material. Specifically, we are talking about the metals. Okay, then line parameters. We do have two types of lines: lossless lines as well as distortionless line. You can look into this table. Okay, in general case, in general transmission line, the gamma, okay, propagation constant is given in this way, and the characteristic impedance is given in this way. Those are very general formulae. If we say that, okay, we have a lossless line, it has a condition: resistance as well as conductance, or I will say that admittance, not conductance, admittance are equal to 0. So put R is equal to 0, okay, as well as G is equal to 0. Okay, so what we will have? J omega L into J omega C. Okay, so J square omega square can be put outside the square root, and LC will be inside the square root, and we will have this imaginary term. So therefore we will say that, okay, real part of this term is 0. And same way we will put R is equal to 0 and J is equal to 0 over here, and we can have this expression, because we will have j omega L upon j omega C, and j omega will cancel out each other. If we say that line is distortionless line, we do have a condition. We do have the proportionate parameters R upon G is equal to L upon C. This is a necessary condition of a distortionless line. So we can have this expression and this expression. Okay. But to get this kind of expression, you need to remember only the general case and the conditions for two different types of lines, lossless and distortionless. You can put the values and get the expected formula while solving the numerical. Okay. So we do have for lossless line, R is equal to G is equal to 0. The transmission line is said to be lossless if the conductors of the lines are perfect, that is conduction current is infinite, and the dielectric medium separating them is lossless. Okay, dielectric medium ka conductivity sigma is always 0, perfect dielectric material. Okay, so therefore alpha is equal to 0, gamma is equal to j beta or j omega root LC, and z is equal to z0 is equal to under root LC. For distortionless lines, we do have R upon L is equal to G upon C. That is a necessary proportionate condition. A distortionless line is one in which the attenuation constant alpha is frequency independent, while phase constant beta is linearly dependent on frequency. Alpha independent है, whereas beta is independent है. Okay, so we can say that, okay, while after putting these conditions into the big formula of alpha and beta, we can arrive at these formulae. You need not to memorize, but yes, if you memorize the bigger formulae by putting the condition, you can derive within 20 or 30 seconds. Then gamma is equal to j beta, that is j omega root LC, and z0 is equal to root R upon G or root L upon C. Okay, proportionality constants. Okay, note that A lossless line is also a distortionless line. Okay, lossless line is also a distortionless line. If you put into this condition 0 upon L is equal to 0 upon C. So definitely 0 is equal to 0. Condition is satisfying. Okay. So a lossless line is also a distortionless line, but a distortionless line is not necessarily lossless line. Okay. It cannot be said in a vice versa condition. लॉसलेस लाइंस आर डिजायरेबल इन पावर ट्रांसमिशन जहां पे लॉस बहुत कम होना चाहिए बट वेयर एज इफ वी कंसीडर द टेलीफोन लाइंस दे नीड्स टू बी डिस्टॉर्शनलेस डिस्टॉर्शन कम से कम होना चाहिए so particularly this slide is very important as long as MCQ kind of examination is concerned. Okay, each and every statement over here is an MCQ. Fine. Let us go for a numerical. Okay, an air line has characteristic impedance of 70 ohm. Okay, we are given with characteristic impedance and a phase constant of 3 radian per meter. So we do have phase constant beta as well at 100 megahertz frequency. Calculate the inductance per meter and the capacitance per meter of the line. Okay, so an airline is can be regarded as lossless line. Okay, क्योंकि air is an dielectric medium and we know that for an air we can say that its conductivity is nearly equal to 0. So it is an example of a lossless line. Okay, hence this is very important. If you are not putting this assumption, we cannot solve the numerical. Hence for a lossless line we know that R is equal to J is equal to 0 and alpha is equal to also 0. We do have characteristic impedance as root L upon C and phase constant beta as omega into root LC. Okay, so dividing this equation by this equation means dividing equation 1 by equation 2, we can get R0 upon beta, okay, is equal to 1 upon omega C, because root L are going to cancel out each other. Or rewriting this equation for C. C is equal to beta upon omega R0 is equal to beta दिया हुआ है, omega is nothing but 2 pi f, okay, and R0 is nothing but 10 raised to 6 into 70. क्यों? क्योंकि root LC, sorry, R0 is something given over here, 10 raised to 6 70 ohm. Okay, this one Z0. Okay, this 100 is this much is your F 100 megahertz and R0 is nothing but Z0 and that is your 70 ohm. So we can get a value of capacitance as 68.2 picofarad per meter, and from equation number 1, okay, let us put your value of C into it. So we can say that 70 is okay. We can say that L is equal to R0 square C. R0 is nothing but a Z0, so 70 square, and C we have just calculated it, and therefore we can have the amount of inductance provided by an air line. Okay, transmission line with air as a dielectric medium, 334.2 nanohenry per meter. A straightforward numerical, but yes, without this understanding, okay, we cannot solve the numerical. Next, you need to zoom in a little. Okay, a distortionless line. Okay, distortionless line यहाँ पे दिया हुआ है. So we do have R upon L is equal to G upon C, has a characteristic impedance Z0 alpha U, that is velocity of propagation. In our case, instead of U we have used V P. Okay, 0.6 C. C is over here, velocity of light. Okay, where C is the speed of the light in vacuum. Find R, L, G, C and lambda at 100 megahertz. All the primary constants we need to find. So for distortionless line, we have R upon L is equal to G upon C, or we can say that RC is equal to GL. Okay, or G is equal to RC upon L, something. And hence, since Z0 is equal to root L upon C, this is a characteristic impedance of a distortionless line. This is alpha for a distortionless line. We can put it in terms of the characteristic impedance. Okay, alpha is equal to under root Rg is equal to R under root C upon L. Why? Because we have placed value of G from here. Okay, so what we have, R square C upon L. R square is taken outside the root, so R under root C upon L. Okay, what is this C upon L? This is nothing but 1 upon Z0, so R upon Z0. Or we can say that, okay, R we can calculate as alpha into Z0. We are just rearranging the equations, twisting them just the way. So over here we know that alpha and we know Z0, therefore we can get R. But Vp is nothing but omega upon beta, is nothing but 1 upon root LC. Okay, we will see how to use this one. So R can be find out as alpha Z0 into alpha is nothing but 20 milliniper. Okay, so 20 into 10 raised to minus 3. Z0 is your 60 ohm. So 60. So R is 1.2 ohm per meter. Dividing equation number 1, okay, by equation number 3. Okay, so we will have dividing equation number 1 by equation number 3. We will have Z0 upon Vp. Z0 upon Vp इसको किया Z0 upon Vp. So we do have this resultant as L. Okay, because these root terms are going to and L comes out outside the square root. So L is equal to Z0 upon Vp is equal to Z0 is our 60. Vp is given as 1 upon root LC, and we can put the values over here. Oh, sorry, Vp is given into the numerical 0.6c, 0.6 into 3 into 10 raised to 8. So we will have the L. So we do have L from the unknown quantities. Now G can be written as alpha square R. How we arrived at this expression? Put it over here, the value of your alpha and rearrange the term. So G is equal to alpha square R. Alpha is given. Now we have calculated R, therefore we can calculate the G. Then multiplying equations. Okay, multiplying equation number 1 and equation number 3 will give us propagation velocity. Velocity of propagation into Z0 is equal to 1 upon C, or we can rewrite C is equal to 1 upon Vp Z0. We have all the values, therefore we can find the capacitance. And at the last, lambda is nothing but velocity of propagation upon frequency. Velocity of propagation is given into the numerical as 0.6 c. C is nothing but 3 into 10 raised to 8, and frequency at 100 megahertz. Okay, 100 megahertz means 100 into 10 raised to 6, or I will say 10 square, or I will say simply 10 raised to 8. So we do have the wavelength of the signal flowing through the transmission line is 1.8 meter. Okay, 1.8 meter. So if you have observed the process, we are just tickling with the formulae. इसमें उसको रखो, उसमें इसमें रखो, वगैरह वगैरह वगैरह. Okay, you need not to really memorize the formula. You just need to rearrange the formula. That's it. Okay, so what you need to memorize while solving the numerical conditions. Conditions for lossless and distortionless lines. You need to memorize general formulae for propagation constant and characteristic impedance, as well as you need to memorize general formulae for alpha and beta. Okay, attenuation and phase constants. And if you memorize these formulae, these will be sufficient minimum necessary formulae for solving the numerical. Okay, and okay, fine. In next session we will see input impedance, and we need to discuss a little about more parameters, Those are for the sake of definition and solving the numerical. And this is very important, general solution. We need to discuss this slide. You are not, you will be not asked to solve or derive these equations, but you need to have the understanding of these equations. ये कहना क्या चाहते हैं, what individual term tells you and what is their significance, okay, over here and over here as well. So we will discuss this part in the next numerical, sorry, next lecture. And power transmission as well, and later on we are going to solve the Smith chart numerical, very important topic as long as descriptive kind of examination is concerned. Okay, so we will require 4 lectures more for finishing unit number 5. Okay, I will stop the recording and